Okay, time to get started. Oh, let's see. Let me double check my. Yeah, okay, good. Okay, so here's what we were talking about last time. It was sort of an alternative interpretation point of view on on vector line integrals, right? So we motivated vector line integrals by this idea of work. But that only really kind of makes sense if the vector field integrand represents forces. So what if the integrand does not represent forces? What if it represents a fluid flow? And what we went through is a sort of a seemingly weird question that we answered, and then we kind of reinterpreted the answer in relation to another question. And our punchline was that vector line integrals represent the extent to which the fluid is flowing along the curve per unit cross-sectional area. Right? Obviously, more area means more of whatever this Q thing is. So factoring out that area, the vector line integral represents the extent to which the fluid is flowing along the curve. A nice little, I mean, it's kind of a weird thing. It's always nice when the interpretation of a mathematical quantity is something familiar. Isn't that great? Right? But what is a vector line integral if it is forces? Work. One word answer, right? Because you already know what that is. So this seems weirder because this is an idea that you haven't previously seen. Right? But it's nevertheless a pretty natural interpretation. And then we generalized that to, or specified that, to the specific case of if you have a closed curve as your domain, then we have a specific choice that we made that we make then for what this represents. It represents what we call circulation. It represents the extent to which the fluid is kind of following around the closed curve. And therefore, you might say the extent to which the fluid is kind of representing a rotation. And then I like to point out that this means, since the extent to which the fluid is flowing, let's say counterclockwise on the edge, tends to correlate with the extent to which it's doing that over the interior, right? I mean, on the small scale, we would expect these to be, roughly the same idea. And so in this case then, circulation is a way of trying to get your hands on the question of which direction are the dead leaves that fall in the river, right? Which direction are they going to be rotating as they go downstream, right? Are they going to be kind of turning counterclockwise like this as they float down the river, or maybe the other direction? Right? Okay. All righty. So moving along. When you want to compute vector line integrals, we have a formula. You can plug and chug. Yes. Plug and chug can be really annoying sometimes, right? A lot of tedium that goes into that. And if there's any clever little shortcuts that allow you to avoid massive amounts of effort, it's well worth trying to notice these things. Right, so this is another. I'm going to say, obscure is the wrong word. This does not work with every vector line integral you're going to need to compute, but it works with a surprisingly large number. Again, I've said it a million times. The world's full of symmetries. Right. Well, the world is also full of fortunate geometry. And I can't quantify how often stuff like this came up for me in my undergrad, but it came up plenty. So just as an example of what I'm talking about, let's consider this example here. And we have a weirdly parametrized curve. Notice that it's sort of spherically parametrized. So I'm giving you formulas for rho, phi, and theta, which means if you want to write down the actual rectangular parameters, if you want to know x, y, and z as functions of t, they're going to be nasty. It's going to be trig of these things that I've just written down here, right? And it's going to be a mess, just a terrible mess. So this is a not very nice curve, right? And we want to compute the circulation. I guess that's not. We want to compute this vector line integral of the vector field f given there on the parametrized curve given here. Okay, so here's the key geometric observation. Here's why geometry is awesome sometimes. Notice, however complicated this may be, right, very conveniently, we are always on the unit sphere. Right? No matter how complicated the story is for phi and theta, rho is always 1. Right? And so here's the geometric observation then. If you are confined to the sphere, if you are moving around exclusively on the sphere, then that means that your dx vector has to be parallel to the sphere. Right? If it was pointing off of the tangent to the sphere, then that would suggest how you're moving away from the sphere. So first geometric observation there, the dx is always parallel to the sphere. And now next observation, let's look at our vector field here, and a little bit of a weird vector field, I suppose. And notice I've written this in kind of a vector notation instead of a coordinate notation. So if you were going to actually write down the coordinates for this, you got to keep in mind that the x vector is x comma y comma z. So the neat observation to make about this is it's always a scalar multiple of position. And position is always perpendicular to the sphere. Right? This is the neat thing about spheres. Right? Radii are always perpendicular to the surface. This is a peculiarity of spheres. Only spheres have this feature. But really nice. And so given that the vector field in question is a scalar multiple of that, then the vector field itself is also always perpendicular to the sphere. Okay, so who cares about all of that? And the reason we care is because what we're interested in is this dot product, right? We're interested, you can see it right here, in the vector line integral we're supposed to compute, f dot dx. Green dot blue. Well, if the vector field is always perpendicular to the sphere and if dx is always parallel to the sphere, then the dot product is always 0. And if the dot product is always 0, then the integral adds up a bunch of zeros. In other words, the integral is 0. So awesome little geometric good fortune stuff like this. Again, you'd be surprised how often stuff like this comes up in the real world. Yeah.
So when solving problems, how much of that information should we provide to how much?
Yeah, great question. So how much to document? In other words, your reasoning. There are no metric units for documentation, so I can't be too precise. But the way I try to communicate that to students is by just examples. And so you'll notice here that I've written down a couple of little quick notes, and it's pretty terse, right? This isn't a horrendous amount of writing to do, but you see I'm documenting all the key ideas, parameterizations on the sphere. Therefore, dx is parallel to the sphere. I mean, it just something along these lines is, I would say, plenty. And the real criterion is going to be, well, what does the grader think, right? And does the grader feel like they can confidently interpret from what you've written that you have an understanding of the ideas that go into the solution, right? So it doesn't take much, and we don't require complete sentences, right? But just want just enough so we know what you're thinking. Yeah, great. Okay, so be on the lookout for this kind of thing. Again, I've commented that symmetry was something like 20% of my physics major was just making symmetry arguments. And that's a lot, right? That's worth always always keep one eye just looking out the side of your field of view. Hey, I wonder if, just always check on that real quick, right? And likewise with this business about fortunate geometry, think about what's nice about my domain. What kind of nice geometric properties does it have? This being a nice example. And is that going to help me capitalize on the question I'm asking? Right? And it takes you a few seconds, and it can pay off big time. Okay, next little topic that has to get said. This is, as far as Math219 is concerned, mostly a notation thing. There are better reasons than this to talk about this subject. But anyway, here's the notational observation. There's our computational formula for dx. You'll notice it's all written in vector notation. But you can write that in coordinates, can't you? That's just multiplying out. There's nothing new, really, in this little, what I have in purple there. That's just kind of plugging in what we know about these things. And so what that gives us, then, is a coordinate point of view on what the dx vector is. So we can now write the dx vector in coordinates. So if you do, write your dx vector in coordinates. And if your vector field... well, you can write that in coordinates too. For whatever reason, arbitrary reason, a vector field F is often we use P, Q, and R to represent the coordinates of the field vector. I'm not really sure where that comes from. Anyway, it's a very common choice. But if you do that, notice then just the matter of kind of dotting out this dot product, right, gives you this. P dx plus Q dy plus R dz. And as such, then, this is a kind of an alternative notation for a vector line integral. Right? If you want to talk about the vector line integral, integral of f dot dx, if you want, you could instead write integral P dx plus Q dy plus R dz. Now, I have a suspicion as to what you're probably thinking right now, which is why on earth would I want to do that? Right? It's a lot more to write out. It takes up more time. It takes up more space on the page. And frankly, in Math219, this isn't going to buy us any. This is not going to extend our capabilities for vector line integrals. It's not going to streamline computations. So why am I showing you a notation that we're not going to use at all? And there's two reasons for this. First of all, is a cultural point here. You may recall I've said a few times that there are various degrees of additional sophistication and power that multivariable calculus can be thought about from. And one of the higher powered ideas that you can include is this idea of differential forms, and it's in our textbook, chapter 8. Right? And if you're curious, you're welcome to look at it. It's not part of Math219. A little too sophisticated, I think. But frankly, differential forms look a lot like this. And differential forms absolutely can increase what you can do. There are crazy powerful things you can accomplish with differential forms. So this notation is not pointless. This notation is really powerful in these other contexts that we're not going to cover in this course. So again, it's kind of a cultural point. I think it's nice to know, even if we're not going to cover something, nice to know that there's more to be known in those areas. The other reason is that, and kind of a connected reason, is that because of this additional power that you can get from differential forms, this notation's in common use. A lot of people like it. Somewhat to my frustration, people like to use this notation not just when it's useful, but even when it doesn't really buy you anything. And so I don't myself, if I'm not going to be using the power of differential forms, I'll just write it like this. It's much more compact. I think more obviously natural. What is F? It's my vector field. Maybe it represents force. Maybe it represents a fluid velocity. It's something that's intrinsic to the problem. Right? What is dx? It's displacement. Again, it's something that's actually happening in the story of the question. So this is all natural. Right? And what is Q? I I mean, there's an answer. It's the second component of the vector field, capital F, that represents something natural. But it itself, by itself, I mean, it's not immediately obvious why that's convenient. So anyway, you're going to see this notation. That's the reality of it. Whether you like it or not, whether I like it or not, you're going to see this notation, so you need to know what to do with it when you see it. And my suggestion along those lines is that whenever you find yourself faced with one of these, if only in your mind, just think of it in this sense here. Just realize that PQR is telling you your vector field. dx, dy, dz is just kind of an expanded way of writing the dx vector. And think of it in these more relatable terms. Okay. All right. Last thing we're going to say about vector line integrals, for the moment anyway, is symmetry theorems. You may have seen this coming. You may have wondered, hey, I wonder if these kinds of integrals can be computed with symmetry. And the answer is kind of. And again, you got to be really careful about this. It is a dangerous little landmine here. For scalar line integrals, the answer is yes. We have this theorem. Odd integrand, symmetric domain, integral is 0. Just like in the other kinds of integrals, you need both conditions to apply. Just like in other applications we've seen of this, they have to both be over the same line. I deliberately write these theorems to lay out on the page exactly the same way to emphasize how they're all the same basic idea. Right? So, great news. Scalar line integrals, symmetry argument, go crazy. It's really convenient computational tool. Very powerful. Okay, here's the bad news. For vector line integrals, there is no odd symmetry theorem. It doesn't work. It just flat does not work. Now, why does it not work? Well, I can just kind of give you a rough picture. Here is a domain that, if you'll, forgive my imperfect drawing skills, is symmetric. It's symmetric over this line right here. And we can talk about how this little piece and this little piece have the same size, ds, and that's all encouraging. Kind of feels like something's going to come together here, but the problem is that in this picture, our integrand is not ds. Our integrand is tds, right? This t vector, oh, I keep making bad color choices. I'll use blue. Okay, so this t vector, part of the integrand, part of the story. And just looking at this exact same scenario, you can see these t vectors, they're not the same. I mean, you see it right there in the picture. Not only are they not the same, they're not the negatives of each other either. They're just different. So if you try to write down an odd symmetry theorem, it's going to crash and burn. It just doesn't work at all. So heads up, please, as much as I love symmetry arguments, don't even try to make a symmetry argument for vector line integrals. Rather, scalar line integrals only. Does that make sense to everybody? Everybody's good there? Okay. All right, on to Green's theorem. This is a big one. This is also our first example of a collection of big theorems that structurally are just like each other. The analogies between Green's theorem and we're eventually going to see something called Gauss's divergence theorem and something called Stokes's curl theorem and something called the fundamental theorem of line integrals, which in some sense has kind of two versions depending on how you count. There's a bunch of these theorems that they all look different. They're all about different geometric scenarios. They happen in different contexts. And structurally, they're all really, really similar. So when you are learning these theorems. Now, this is a personal belief of mine. Certainly, the following was very, very true for me. Seeing how these theorems are all structurally so analogous, so similar, is very effective in helping you learn the individual theorems, right? If you understand how Green's theorem is so much like the divergence theorem, and what you know about Green's theorem will help you understand the divergence theorem, right? And Stokes' theorem, etc. Right? So I'm going to put heavy focus, because of that, not just on what is the theorem, right? But what is the point of view on this theorem that makes those similarities as obvious as possible, right? So I could just write down a formula here, right? But then you wouldn't understand what's going on. You wouldn't be able to see how they are all kind of closely related to each other. You'd be missing a lot of conceptual ideas, and your understanding would be just constantly plagued by that shortfall. So anyway, lots of ideas incoming for really important reasons. Okay, where did I put my? Here it is. Okay, so there's a lot that we have to build up in order to be able to get to Green's theorem, in order to be able to see it from this point of view. A lot of this is going to seem arbitrary, and I guess it's kind of arbitrary. But these seemingly arbitrary things that I'm going to throw at you are essential to making the puzzle pieces fit together, right? So we can get some nice dovetail joints and everything just works. Only if we set things up just so. All right, so let's talk about what a boundary is. And I think, loosely speaking, y'all know what a boundary is, right? I mean, if I have some region, and now this is just part of the region. Imagine the region extends, is much larger, or whatever. But I'm just drawing just a small portion. Boundary is, well, it's the edge, right? It's the dividing line between D and not D. Right? It's a pretty fundamental natural geometric idea. I'm going to go ahead and assume you know this idea of sort of a border, I guess you might call it. Okay. We're going to have to adjust that idea in this course. Henceforth, the word boundary is a loaded word. The word boundary now no longer just means, the border. The boundary is now an oriented thing. The boundary now has a direction. The direction of the boundary is specifically that way, specifically not the other way. Okay, so that's a little bit of a weird idea to think of boundary as an oriented thing. It's we don't do such a thing anywhere you've seen previously, I would bet. Right? So what is the correct direction? What is the inferred, implied orientation on a boundary? And there's a nice simple rule. And the orientation is the direction, so that as you move in that direction, the region is on your left. All right, now you have to kind of use your imagination here, but imagine that this boundary curve right here, imagine that's like a little footpath, right? You're going to walk along that path. There's two different directions you could walk on that path. The direction I have indicated here, if you're walking in that direction, the region's on your left. Everybody see that? So that's the rule. A lot of students like to oversimplify and say, oh, okay, so I should always walk to the right. No. It's not always to the right, because check it out. In this case, boundary being what it is, you'd have to go to your left in order to have the region on your left. Right? So it's not as simple as always left, always right. But whatever direction you're walking, the region is on your left. Now, here's another oversimplification that students like to do. And this is less not true, still a little not true. A lot of people think that, okay, well, always counterclockwise. Because always counterclockwise, indeed, would have the region always being on your left. So it seems, right? But not so. And so look at this case over here. If I am at, let's say, a point like this, walking along that little footpath, as it were, that is that part of the border, all right? You'd have to go clockwise to have the region be on your left. Clockwise, not counterclockwise. Everybody see how that this, again, it's all little. The geometry is always a little different for every domain. So try not to oversimplify too much. To borrow a phrase, things should be as simple as possible, but no simpler. Right? And this idea of counterclockwise just isn't quite true. Now, what is true is that if your region is, an easy one, just a blob, no little cookie cutter cutouts in the middle of it, right? Just what we call simply connected. Right? Then in that case, yes, it is true that the correct direction is always counterclockwise, but only in that special case. So anyway, just be careful. How we doing? Arbitrary, seemingly made up, seemingly no apparent reason. There are really good reasons why we choose this on the left rule, and those reasons are beyond the scope of this course. But roughly speaking, it's for compatibility reasons. Okay, so that's the first thing we need to know. Next, really deep idea, this idea of accumulation. Now, y'all heard me talk a lot about accumulating quantities throughout this course, right? One of my favorite things to talk about is that if you are going to use an integral to compute the mass of something or to compute the number of bacteria on the surface of something, whatever it might be, the integrand is a density, right? And the quantity itself has to be an accumulating quantity. The whole is the sum of the parts, right? Every integral you've ever computed anything with, that integral computes a whole as the sum of the parts, and that's what we mean by an accumulating quantity. So to be precise, if you have a region like this, whatever your quantity is for that whole needs to be the sum of whatever the quantity is on this left piece plus whatever the quantity is for this right piece. Now you can see mass works great for this, right? The mass in the whole lump is no problem the mass on the left plus the mass on the right. That's how mass works, right? It's tempting to say, well, what a silly little triviality we're discussing here. Doesn't everything work that way? Be careful. You can talk about physical quantities. Physical stuff tends to have this feature. But let's think about perimeter. Perimeter, I claim, is not an accumulating quantity because the perimeter of the whole, there's the perimeter of the whole. You could measure off what's that total distance along that outside border. That perimeter is not the sum of that perimeter, namely the perimeter of the left chunk, and this perimeter, namely the perimeter of the right chunk. There's extra perimeter in the middle here. Twice. That's not part of the perimeter of the whole. Right? So you just got to be really, really careful. If you're going to use an integral to compute something, you'd better make sure that quantity you're computing is an accumulating quantity. Mass is. Perimeter is not. Is everybody on board? Okay. So here's a weird one. An unexpectedly accumulating quantity. Boundary circulation. Really surprising. I mean, I'm going to show you why momentarily, but It just kind of seemingly comes out of nowhere. So here we go. I claim boundary circulation accumulates. All right. Well, let's look at the boundary circulation around the left chunk. Right. The boundary of D1. Right. Circulation around the boundary of D1 would have sort of these two pieces, right? This is part of the boundary of D1. That's part of the boundary of D1. Note the orientations. D1 on my left for both pieces. Okay, well, let's see here then. What about the right piece? The boundary circulation on the right piece. Well, here's part of the boundary of D2. D2 on my left. Here's another part of the boundary of D2. D2 on my left. And so this is D2's boundary circulation, yeah.
Can you go over the on the left? I'm lost.
Oh, sure. Well, yeah. So just you want to imagine, as you're walking along. So think of the region as being like a little pond, right? And so here, let me shade this blue to emphasize that this is a pond, right? And this is the little walkway that goes around the pond, right? So there's two different directions you can walk on that walkway. And I claim if you're going that way, then the pond's on your right? But if you walk this way, then the pond is on your left. So always go whichever direction puts the thing whose boundary you're talking about on the left. Is that cool?
Yeah, that's cool. Thank
you. Yeah. No worries. Okay. Let's see here. Yeah. Okay, so I'm making this outrageous claim that for any vector field, boundary circulation accumulates. So I've got, in green here, I have the boundary circulation of D1. In the orange here, I have the boundary circulation on D2. And now let's look at the whole. And keeping in mind that the whole is the whole shebang here. Right, and let's talk about the boundary circulation. Well, the boundary circulation is, there's that piece, and then there's kind of that piece. This purple curve, it represents the boundary of the entire solid, like so. And I claim, doesn't look like it, but I claim that these actually add up to the same thing. Green plus orange indeed is purple. In this case. Now, you can see a lot of this is sort of clear, like you look at the green and the purple here and they just track each other perfectly, and then likewise over here, the orange and the purple track each other perfectly, and so I'm going to momentarily just kind of cancel those from both sides of the hoped for equation, and you can see that this is kind of the leftover. This is the problem. What I have here is what's on the left side of my equation, but it's not on the right side of my equation, and this seems to be the reason why these are not equal. But keep in mind, what we have here are two line integrals on the same line segment going opposite directions, which, as we saw last time, means that these two line integrals are negatives of each other, which means that they cancel. And so this problem here, the entire problem cancels with itself, goes away, and there's no distinction remaining, right? So these two, this sum and this whole, are the same. Is everybody on board with that? Yes?
Would this only work if there's if there's uniform field?
No, this works for any vector field. Now, look, my little geometric picture, there's only so much I can put into the picture, right? But when I write, for example, this, what I'm talking about is a vector line integral of our vector field, whatever it is, dot dx, integral over that curve. So I can't. I guess I could technically, but if I were to draw the vector field on this picture, it would really make the picture sort of more complicated. But the point is, anywhere you might be on this curve, well, the vector field, whatever it is, that's what it is at that point. right? And it's the same as you go up as it is as you go down. So on that integral versus on this integral, here, we are looking at, whatever the vector field might be, it's that same vector field for both of these integrals. Is that cool? Yeah. Okay. All right, so this is a really surprising fact. It's a really important fact. This is one of the, if I had to pick, a short list, a Mount Rushmore of most important ideas for understanding vector calculus, this idea of accumulation is on that Mount Rushmore for me. Okay, so boundary circulation is eyebrow-raisingly interesting because of this fact that it accumulates. Okay. All right, now you may be thinking to yourself, okay, well that's all well and good. You just cut that into 2 pieces. What if you cut it into a bazillion pieces? Something more like this. And good news, the whole thing still works. So, for example, if I were to, take my whole solid and break it into a bunch of pieces, kind of like this. Some of these pieces are going to be weird little sort of edge pieces. This is the sad little piece of pizza that, when they cut it rectangularly, you get these little disappointing things here, et cetera, et cetera. There's various weird shapes, right, that your whole gets cut up into. But notice, on all of these pieces, so for example, on this piece here, we're going to be going that direction along that edge, because that's how boundaries work. But wait a second, as part of the boundary of this piece, we're going to be going along the exact same edge. That's that same edge, the sort of the border between this square and that square. Same exact edge, just that now, the way boundaries work, we're going the other way. So this interior edge appears twice as part of the boundary of the pieces on each side, always with opposite orientations, always cancels. Right? So to sort of put it all together, this edge appears twice with opposite orientations and cancels. This edge appears twice with opposite orientations and cancels. This edge appears twice with opposite orientations and cancels, etc., etc. That cancels, that cancels, that cancels, that cancels. There's so many pieces here that just cancel. Now, what doesn't cancel? This edge right here. Right? This edge is part of the boundary of this piece, but there is no piece on the other side for it to be part of the boundary of, because our region ends here, because this is part of the boundary of the whole. So that stays there. There's nothing to cancel with. Likewise, that piece. Likewise, that tiny little piece. Likewise, that and that and that. And you can see all the interior pieces are going to cancel. All of the edge pieces are not going to cancel exactly as we need it to. And you can make up a notation and do all this algebraically, and it all totally works. But that's a sort of intimidating amount of notation just to document what I think are much more satisfying to see geometrically. Is everybody buying this? Okay. All right, now here's a creepy idea. This is a weird one. I'm going to ask you to use your imagination in a certain way. Accumulating quantities. Let's think about various different accumulating quantities we've talked about. My favorite is mass. It's visceral, right? We stub our toe on it all the time. We have extensive experience with mass. We have great intuition for mass. And mass, in addition to being an accumulating quantity, has location. Right? So, for example, if I talk about the amount of mass over this whole, the grand total of this lumpy whatever that thing is, if I talk about the amount of mass total, Well, that is going to be the mass of that chunk plus the mass of this chunk plus the mass of this chunk plus the mass of this chunk plus the mass of that chunk, etc., etc., etc. So, in particular, I can talk about, of this whole that I have, of this entire whole, I can talk about how much of that whole is in this chunk right here. Right? And you want to know how much of the mass is in there? Fine. Compute the amount of mass that's on that peak. It just is what it is. You can just measure it. So mass can be thought of as having specific locations because of this fact that it's an accumulating quantity. And now here's the first version of how I'm going to try to apply that idea now to boundary circulation. Boundary circulation is a whole, and I'm making this weird suggestion that I can talk about how much of that whole is in this rectangle here just by computing that circulation. And that seems like a ridiculous statement. Let's just focus for a second on why this is ridiculous. This boundary circulation on the outside is measured entirely out here. It's not even measured over here. What would I mean by saying that some of this circulation is in this circulation? It seems to be just a disconnect, right? But keep in mind, these are quantities that are defined for pieces of area, right? When I compute, or if I talk about the boundary circulation being this, don't forget, what I'm really doing is I'm talking about that as being the boundary of this whole. So what I'm really saying when I say boundary circulation, I know we like to draw pictures about where the computation is actually performed, but boundary circulation is a feature of this solid, this whole region. And the boundary circulation on this region plus the boundary circulation on this region plus the boundary circulation on that region plus the boundary circulation on this region, right? We know that these add up the way they're supposed to because we already know that this is an accumulating quantity. And so in the same way that I can talk about how much of mass of the whole is inside that piece by, well, just compute the mass in that piece. Likewise, because of the accumulation feature, if you want to know how much of the whole boundary circulation is on that piece, well, just compute the boundary circulation on that piece. So, very strange idea. Give me 2 seconds. So, boundary circulation has location, and as such, it behaves like stuff. It behaves like mass does. You can think of boundary circulation as being a physical quantity. It isn't. It's not a physical quantity. But it behaves like a physical quantity, so you can treat it like a physical quantity, because treating it like a physical quantity just means you're going to be taking advantage of the fact that it behaves like a physical quantity. Somebody had a hand up over here. Yes?
So in the last diagram, we saw how some of the circulation cancels out next to boundary wise.
Yeah.
In this case, doesn't the middle
area
doesn't cancel out with the
no, that
area?
You're absolutely right. So as I'm computing the boundary circulation on this chunk here, you are right that I'm going to be computing, for example, a line integral sort of like that. Right? And as part of computing the boundary circulation on this piece, I will be computing an integral kind of like that. And yes, indeed, these two things do cancel. The fact that they cancel is why, in some sense, it's the whole point. That's why I can claim the whole is the sum of the parts. Right? But the parts still exist on their own. It's just that in some sense, all of this boundary circulation is going to cancel with stuff that's going to be on the surrounding pieces. That's why it behaves the way it behaves, right? But nevertheless, the circulation on this piece by itself is still a sum of 4 line segments, and it still is a thing. Before it cancels, it's a thing, and then it cancels and makes the accumulation. Is that cool? Yeah. All right. Okay, so here's the nice, I'm going to say really important takeaway, and that is you should view boundary circulation as kind of being sort of physical, even though it's not. Okay. All right. Okay, here's the thing about stuff. If you have stuff, you can talk about stuff per unit size, aka density, right? And so now here's our first very familiar notion of density, mass per unit size, right? So I can talk about, any given little rectangle, there's this accumulating quantity called mass. I can therefore talk about how much mass is in this region individually. And I can talk about the area of that little region, and therefore I can talk about how much mass is in here per unit area in here, and that's this idea of a density, right? And this is we've seen various different kinds of densities. We've seen mass density and population density, and different, anyway, various different versions of this. Right? Okay, so here's the creepy idea. Circulation, boundary circulation, is also an accumulating quantity. So I can talk, it sounds weird, I know, but I can talk about how much boundary circulation there is on that piece. And you're going to want to visualize that by way of, thinking about the integral happening on the boundary there. But again, that's a little bit of a red herring. The fact that it's computed on the boundary is not the point. The point is that boundary circulation is something that we associate to that region. And so I can talk about how much boundary circulation there is in that region. And I can talk about the area of that region. And therefore, I can talk about boundary circulation per unit area, a.k.a. in the same way that we call this mass density, right? And analogously, when we're talking about population, we talk about population density. Here, my accumulating quantity is circulation. And so I'm going to be using this term, circulation density. All right? Is that cool? I know it's psychologically a little bit of a stretch. Seems like a weird thing. Again, we're viewing this circulation as being stuff, and that's seemingly very strange. Here's the good news. There's a formula and several notational options for circulation density. Here's the formula. dq dx minus dp dy. Boom. Now, why does this formula work? Well, you can write down, there's a computation you can do. The computation's in the book. The computation's important in the sense of if you want to be rigorous and check all the details, then yes, that's an important computation. For what we're doing here, I know y'all are engineers, right? And I think what y'all most need out of a class like this is a sense for what are these things, right? So that's why I'm spending all this time talking about viewing circulation as being an accumulating quantity, viewing it as being distributed over the interior, right? Because that's important conceptual ideas that are going to help you kind of have an intuition and develop a working proficiency with using these ideas. This computation, I'm going to call it detail from that point of view. So you can read it in the book if you like, but it's not really that big of a deal. Various notational options that you can consider. I'm going to color this one here in red and put a frowny face because this one bugs me for reasons that I don't have time to talk about. But various different ways that you can write and refer to circulation density. And it looks like we're out of time. Sounds like we're out of time anyway. So I'm going to go ahead and draw the line right there, and we'll have a big, exciting conclusion on Friday. See y'all later. Have a good one.